Have you ever watched something move, like a car speeding up, a ball flying through the air, or even just your phone slipping out of your hand, and wondered what's really going on there? Well, these aren't just random events, they're actually solvable mysteries. And today, we're going to become motion detectives. Our weapon of choice? A powerful set of tools known as the kinematic equations. Seriously, think about that for a second. That heart-stopping moment your phone is in free fall, we can actually figure out its exact speed just before impact. And we don't need any fancy equipment to do it. This is exactly the kind of everyday mystery that kinematics is perfect for solving. Okay, so to crack any case, you need the facts, right? In motion physics, these are 4 key clues. First up, displacement. That's just fancy talk for how far something is moved from its starting point. Then we've got velocity, which is its speed and its direction. Acceleration tells us if that velocity is changing. And finally, time, which is, how long the whole thing takes. If we have a few of these, we can pretty much always find the ones we're missing. Now, before we bust open our toolkit, there is one single golden rule we have to talk about. It is the absolute key to making any of these equations work. It's a total non-negotiable. And that rule is constant acceleration. All this means is that our object's velocity has to change in a nice, smooth, predictable way. It's not speeding up randomly, it's changing its speed by the exact same amount every single second. This assumption is the foundation for everything we're about to do. So what's the perfect, real-world example of this? Free fall. Pretty much any object falling near the Earth's surface does so with a constant acceleration. Now, to keep things simple, we're going to pretend air resistance doesn't exist. It just makes solving the case a whole lot cleaner. And that special constant acceleration even has a name. We call it g. It's about 9.81 meters per second squared. What that really means is for every second something is falling, its speed increases by 9.81 meters per second. This number is going to be one of our most trusted clues. All right, we've got the golden rule down. It is time to open up the detective's toolkit. We have 4 main equations, and here's the really brilliant part. Each one is specifically designed for a situation where one of our 4 key clues is totally missing from the case file. So let's say you're looking at a problem, and you have no idea how far the object traveled, and you don't even need to know. Well, this is your go-to tool. It connects final velocity, initial velocity, acceleration, and time, without ever having to worry about displacement. Okay, what if acceleration is the mystery? The problem doesn't mention it, you don't need to find it. In that case, you pull out the second tool. It lets you find the displacement by just using the average of the initial and final velocities and multiplying by time. Super handy when acceleration is the missing piece. And tool number 3, this is the one you grab when you don't know and you don't care what the final velocity is. It connects displacement directly to the starting velocity, time, and acceleration. And finally, our 4th tool. This one is seriously powerful because it lets you solve the mystery without knowing how long it took. If you don't have a stopwatch for your case, this is your equation. It connects all the other variables and lets you bypass time completely. Theory is great and all, but these tools are pretty useless if they just sit in the box. So, let's get our hands dirty. Let's take what we've learned and actually crack a real-world case. Here's our case file. We've got a skater. They're cruising along at 5 meters per second. They hit the brakes and they come to a complete stop over a distance of 23 meters. The mystery we need to solve is, how long did that take? Okay, first step for any good detective, organize the evidence. So let's list out our clues. We know the initial velocity, or v0, is 5 meters per second. We know the final velocity is 0, because they stopped. And the displacement is 23 meters. The one thing we're looking for? Time. So take a look at our list of knowns and the one unknown. Out of our 4 main variables, displacement, velocity, acceleration, and time, which one is completely absent from this case? That's right, we don't know anything about acceleration. So which tool from our kit works without it? This leads us straight to tool number 2. It is the absolute perfect fit for this job. It connects our 3 known clues, displacement, initial velocity, and final velocity, with our one unknown, time. We have everything we need to solve this. So we just plug in our numbers, do a quick bit of algebra to rearrange the equation, and we get our answer, 11.6 seconds. And just like that, by picking the right tool, the mystery is solved. Case closed. So far, we've only cracked cases that happen in a straight line. But let's be honest, the world is more interesting than that. What about something like a baseball flying through the air in a big arc? Do we have to throw out our whole toolkit? Absolutely not. We just have to be a little more clever about how we use it.
And here is the big secret. We take one complicated 2D problem and we break it into two much simpler 1D problems. We look at the horizontal motion and then we look at the vertical motion, completely separately.
And this is why that works so beautifully. Think about it. Horizontally, after you throw a ball, is anything pushing or pulling on it sideways? Nope. So its horizontal acceleration is 0. It just cruises along at a constant speed. But vertically? Oh yeah. Gravity is on the case the whole time, accelerating it downwards at our old friend 9.81 meters per second squared. So we can literally just apply our same 4 tools to each direction. We just add little x and y subscripts to keep things organized. And what's the one variable that connects these two separate stories? It's time. Time flows the same for both the horizontal and vertical parts of the journey. It's the bridge that links them together.
And this isn't just some clever trick, it's a fundamental concept in physics. As our source material from Pasco Scientific puts it so perfectly, the motions along a perpendicular axis are independent. What happens up and down has no effect on what happens left and right, and vice versa.
Isn't that amazing? We don't need a bigger, more complicated toolkit. Those same 4 essential tools that we started with are powerful enough to describe the graceful, complex arc of a projectile. We just have to use them twice. So, we've cracked straight-line motion, we've cracked motion through the air, we've built an incredible foundation. But the mystery doesn't end here, because things don't just move from point A to point B. What about rotation? What happens when an object starts to spin? Well, that's a whole other mystery for another time.